Welcome, chemists. Today we are going to be going over the math that helps explain the KMT theory from our last lesson. We will be focusing on three main topics: Graham's law, kinetic energy equations, and different conversions involving temperature and pressure. A first look at this slide might be a little daunting. Graham's law is talking about how fast a gas can go or how far it can travel based on its mass. So the mass of the gas is going to matter for Graham's law. And there's a couple, Graham's law can be displayed a couple different ways, and you can see that here on the left. There's even another way we could just display that. But what you need to know is on the right, what molar mass is. And I believe you've learned that before, but molar mass is the mass of the molecule where you add up all of the individual parts. So you can see that CH4 is made up of one carbon, the one is not visible, and 4 hydrogens. So you go to the periodic table and you take a look at the mass below the atom, and since there's one carbon, you add one carbon, the mass of one carbon, and since there's 4 hydrogens, you multiply that mass by 4 and you add them up and you get that 1605 is the molar mass. You don't really have to know what the word mole means. We'll talk about that at a different unit, but that is the mass that you are going to be using for Graham's law. So we're going to need that periodic table to help do Graham's law equations. Here you can see the 3 different ways you can use Graham's laws. The first one, where you're looking at velocity and masses. The second one, you're looking at rates, which is how fast they're traveling per time, and masses. And then the third one is the molar masses and the distance that they travel. And you'll notice that you're going to see that there's VA or rate A or molar mass A. The A and the B don't really matter. They just mean one thing, and then B can be the other thing. So when you're looking at your gases, you can see that for like the first one, the velocity of A goes here, but the mass of A goes here. So if we're looking at this first problem, chlorine gas, it doesn't matter which way you describe it. If that's chlorine is going to be the A or the B, you just have to be consistent. So a sample of chlorine gas diffuses, so we know what that means from the last topic, and travels a distance of 25 meters in a given amount of time. How far would methane travel in that same amount of time? Okay, and then I would give you the molar masses. So you know that chlorine, so Cl2, travels 25 meters. And you're trying to find how far CH4 can travel. And you don't know that. So you can see, you look up to the top and say, oh, I need to use this equation. So we have the molar mass of B. So let's just describe chlorine as A, and let's describe methane as B. So then the molar mass of B is CH4, and I identify that. So the square root of 16.05 grams per mole. We'll use the units. We'll talk more about that later. Let me just write that a little bit nicer. The square root of 16.05 grams per mole over the square root of 70.9 grams per mole equals, now we have the distance A, and we said A is chlorine, so chlorine traveled 25 meters, and so you're looking for your distance B. Okay, now you can just use algebra to solve for that distance B. After doing that algebra, you get the answer of 52.55 meters for the distance that B is going to travel. And it's important to have the units, and you might have rounded slightly. If you didn't get that answer, check how you plugged into the calculator, make sure you have your parentheses right. But what's important to notice is, does that make sense? So chlorine is much heavier than methane. So which is going to travel farther? Is the chlorine going to travel farther or the methane? Since the methane is less heavy or has less mass, you would expect that to travel farther, and in reality it did. So that checks off. We can work on the second problem. So let's take a look at the second problem. Here we can see that we are dealing with rates, so we're going to be using this equation. And we have oxygen, so let's just call oxygen the A. And we have an unknown gas, so we're going to call that B. So we know that A rate equals 461.2, B rate equals 632.00, and we are looking for B mass, question mark, and we know B mass of oxygen, and it's O2, so we can look that on the periodic table, and we can see that it is going to be 16. So then we plug the numbers in. So the rate of A, 461.2, divided by rate B, 632.0, equals the square root of the molar masses. So molar mass of B we don't know, so we're going to put X as our variable, divided by the square root of what we do know, and we know that's 16. So then you can go ahead and solve that one for X, which is our unknown mass. When you do that, you should get something around 8.52. And what are the units? Well, molar mass is unit of grams per mole. Okay. And then you could go ahead and then try to find the unknown identity, but we're not going to get into that right now. So hopefully those examples worked. If you didn't get that answer, remember squaring something is the opposite of the square root, so that might have been your problem. The next thing we have to take a look at is finding average kinetic energy. And we've said before that temperature is a measure of average kinetic energy. So at any given temperature, let's say 25 degrees, all three samples of gases in these different balloons are going to have the same average kinetic energy. But the picture is supposed to show that they might also have different masses. And so if they have different masses, they're going to have different velocities. And so the equation we're going to look at helps you solve for velocity. So here's a throwback from physical science. The kinetic energy equation is Ke equals 1/2 mv squared. So when we're reading the problem, we want to first identify all those variables so we can see that butane, which we don't really need to know, is moving at a velocity of 676 meters per second. And that we know the mass, it's really tiny, 9.65. I'm going to write E because it's simpler, E, which means times 10, so that E means times 10. You'll use that in your calculator, to the negative 23, okay? And so we want to find the kinetic energy. So we want to know Ke equals question mark. So we know the formula equals Ke equals 1/2 mv squared. So let's plug it in. Ke equals 1/2, sorry, the picture, 1/2 m, so 9.65 E to the negative 23rd times V, running out of room here, sorry, 676 squared. Okay, so when you plug that into your calculator, you can solve for Ke equals. So if you plug that into your calculator correctly, you should get something like, oh shoot, I just deleted. And if you enter that information into your calculator, be careful how you enter the E to the negative 23. You're going to get 2.2 E to the negative 17 joules, which is obviously not a lot of energy, but we're talking about one molecule of butane. So there's going to be lots of molecules of butane, thus it's going to have a lot of energy. Without doing any real math, we can think about this question as well, referencing this equation right here, K equals mv squared. So all of these are going to have the same kinetic energy, so you can essentially think of them that their mv squared is going to equal the mv squared, which is going to equal the mv squared. So which one is going to have the highest velocity? Well, if they're all being equal and you kind of put in the masses, you can understand that these molecules will have the highest velocity because they have the least mass. So because the mass is down, thus it's going to bring the velocity up. We can represent the same question in a slightly different way. You see here that these arrows are longer than those arrows, thus this represents a bigger speed. So if this one has more velocity, that means it has to have less mass comparatively. For the lower velocity, that's going to have a higher mass. Okay, so when one goes up, the other one goes down, with all things being equal. Okay, so it didn't really matter exactly what temperature they were at. Now, the great physicist Ludwig Boltzmann came up with another equation, and he dealt more with thermodynamics, which is talking about energy, but here's kinetic energy, so this is where he fits in. He's got this equation right here, Ke equals 1/2, let me just resize that. Sorry, K equals 3/2 Kb times T. T being the temperature in Kelvin, that's really important, and the Boltzmann constant. So a constant is just a number in math that's going to remain the same, and it has units that are going to allow the mathematical expression to be carried out. So we can read this sample problem, and it says a gas molecule produced in your stomach. Sorry, my face is covering the problem. Let's move me over here. So a gas molecule produced in your stomach is at your body temperature, which is 310 Kelvin. How much kinetic energy does this molecule have? Now, we'll never make you memorize a constant. So a constant, this is always something we're going to give you. So we're just asking for kinetic energy. So we're looking for Ke equals question mark. And we have the Boltzmann constant right here. And the problem gave us the temperature of 310, so you can just plug it in. Ke equals 3/2 Kb, so that's that Boltzmann constant, 1.38 times 10 to the negative 23. It's joules per Kelvin. And then let's just put parentheses here, and then times the temperature, which is 310 Kelvin. Hopefully you remember from last year, because those units are on the top and the bottom, they will mathematically cancel. And so our product is going to be left in joules when we do that math. So take a second, plug that into the calculator, and see what you get. Here's a slightly more difficult problem for you. Here we're asking again for what is the velocity of a certain gas molecule. Now, you can see, sorry, I have to quickly plug in my pen. You can see that velocity is in this equation right here, so we can solve for it using that, but nowhere in the problem did it give us the kinetic energy, right? All it gave us was the mass and the temperature, okay? So how are we going to find the velocity? Well, what you can do is take the fact that because both mv squared and 3/2 kbt, both of these are equal to kinetic energy, that makes them equal to each other. So thus you can then set mv squared equals 3/2 kbt. Sorry, that should be a lowercase b. Or down below, sorry, 3/2 kbt. So now we can solve for v right here, and we know that the mass is right here, and we know kb. We can go back to the other page and look at the Boltzmann's constant, and we have the temperature right here, and thus it's just a matter of rearranging and solving for V, so you're eventually going to get the equation V equals KBT over M, and it's going to be the square root of that answer. And so you can go ahead and rearrange that equation, plug those numbers in, and solve for that velocity of the gas molecule. In this class, we will be avoiding Fahrenheit as much as possible. There's a couple times that we will use it, but basically we'll be using Celsius and Kelvin depending on what type of equations we're going to use. And so we just need to convert it. And the conversion between Kelvin and Celsius is really easy. You're just adding or subtracting 273.15. That's a unitless, and it gives you Kelvin. Kelvin, again, is not degrees Kelvin. It's just in Kelvin. So I think that math should be really easy as well. We'll always give you these formulas, so you don't have to worry about that. If you have a Fahrenheit temperature and you need to put it into Celsius, you'll use this equation right down here, and you can arrange it to solve for C or F, depending on what you're going to do. So you just need to make sure you're aware of how to use these conversions to go back and forth. And here's a nice chart. Without even doing the math, it would be really good to have this rough estimate. So if I say 20 degrees Celsius, what is that in Fahrenheit? What is that in Kelvin? So whenever you're doing the problems, you can make sure your answers are reasonable. And this is important to know, because if we just, units are so important, because if we just say 100 degrees, that means very different things. And if we say 0 degrees, that means very different things. So we want to make sure you always put units on the problems. So take a second to practice and convert these correctly. Hopefully you got these temperatures for these practice problems. So far we've looked at kinetic energy and velocity. We've also talked about conversions. Now we need to finalize this lesson with pressure and how pressure is measured. Scientifically, we talked about it's the force per area, but we're thinking of it more all of the different collisions added up of the molecules hitting off the wall. And so this can be measured with a variety of different techniques, and so there's different units associated with this. It's all the same pressure, but it's just based on whatever situation is being used, you might measure it a different way, so there will be different units. So we have to learn how to convert between those two. Throughout my life, I've actually been paying attention to this, and I have seen almost all of these different conversions in various places, whether we're looking at a car, whether we're at the hospital, whether I'm looking at a scientific piece of equipment. I've seen most of these different units actually being used still. Some not, but most of them. And so let me just quickly go down the line and mention or say all of these. So we have atmospheres, kPa, so I think of that as 101.3 kDWB, but kPa stands for kilopascals, or we could have just pascals. Millimeters of mercury, that's one of the original ways to measure pressure. Torrs, pounds per square inch, or you might know this as PSI. So I'm going to write that PSI. That's one you should be familiar with. Inches of mercury, very similar to millimeters of mercury, and then finally bar, and you can think of barometer. So these are all different pressure values, and they're all equal to each other, just like you would say that 12 eggs equals 1 dozen. Okay? So these are all equal to each other, so you just have to convert from one to another. So let's maybe do some practice problems. One thing we are sticklers about here at Minnetonka is using dimensional analysis, because it is the one way to guarantee that you will get the correct answer. And so in every single problem where you have a conversion, we need to see the dimensional analysis. Why? Because it allows us to see your thinking, your thought process. It also allows us to give you partial credit. And in time, it will then help you build good habits so you can better problem solve any math problem. So how to do that is you always start with whatever you're given. Okay, so in this problem, we're converting 12 atmospheres to millimeters of mercury. So you always start with what you're given up top. And then you write the equivalence fraction, so the two things that are equal to each other, next to it. So back in the last slide, you saw that 760 millimeters of mercury is equal to 1 atmosphere. Now, we put atmospheres on the bottom because atmospheres are over here on the top. And in math, you know that like 4 times 5 divided by 4 is just going to be 5. Why? Because when you have something on the top and the bottom, they cancel it out. So you strategically set up this problem so your units cancel out. So when you divide atmospheres divided by atmospheres, they disappear and you're left with just millimeters of mercury. So this fact, and again, you will never have to memorize this. This will be in some kind of chart for you. You start with what you're given, you put the equivalence fraction, and you just choose which one goes on the top and the bottom by canceling out the other one. So in this case, we're trying to get rid of atmospheres, and we're trying to convert it to millimeters of mercury. So you multiply them, atmospheres divided by atmospheres cancels out, and then you do 12 times 760 times millimeters of mercury times 1, and you get your conversion. So we want to see that dimensional analysis in every problem in order to get full credit. Tessa, do you agree? She agrees. Okay. So here are some opportunities for you to practice this. The conversions are all right here. I want to see if you can do the correct dimensional analysis. So in just a second, pause it, see if you can do it yourself, and then hit play, and I'll have the answers for you. Let me do one of those problems for you first so you can watch me walk through it. So here we're given millimeters of mercury, and we're trying to get them into HChem. So you always start with what you're given, 180 millimeters of mercury. Okay, it's important to write these units down. There's a couple ways you can do it. You can write the multiplication, and then you can write the fraction. Myself and a bunch of other teachers have been taught, and we like the system where you go like this. So you're making kind of a top level and a bottom level, and you're being kind of put together kind of like a train car. So 188 millimeters of mercury, and we're trying to get them to atmospheres. So we know right away I should write mmHg down here because it's on the top and it's now going to be on the bottom, so it's going to cancel out. And I'm looking for atmospheres, so I put atmospheres up top. Then I'm going over to this chart and I'm taking a look, and I see 1 atmosphere is equal to, right here, 760 millimeters of mercury. So then when you're doing this math, now millimeters of mercury cancels out at top and the bottom, and we're left with the unit we want. So then you just do the math, 180 times 1 divided by 760. The answer is 0.237. And what are the units? Well, mercury divided by mercury canceled out, so your units are in just an atmosphere. Okay, so that's the process you would go about doing. Hopefully those are the answers you gave and the work that you showed. Overall, we know this was a long video, but you could use this video in a variety of different ways to help make sure you know the process.